Hello learners, welcome to this course on practical machine learning using Google Colab. In this tutorial, I will be describing about a very popular algorithm known as Canny edge detection algorithm. We will also look into the implementation part. So Canny edge detection algorithm is used to identify edges in an images. So if the image contains some object, we can find the outline of the object or edge of an object. And the corresponding code related to this Canny edge detection algorithm is available in the GitHub repository link given at the below. You can download the code and make use of it. Let us start with the Canny edge detection algorithm. So as I earlier pointed out, Canny edge detection algorithm is used to detect a wide range of edges. So what do you mean by an edge? A change in intensity or a discontinuity in the pixel intensity or a sharp difference and change in pixel values are termed as an edge. So there are different types of edges which can be identified by using this Canny edge detector. So some of them are detailed here. So the first, I have a step edge. So step edge means an abrupt change in intensity, a sudden change in an intensity. For example, if I have a pixel with a value of something like 0 and the subsequent pixel or the nearby pixel is having a value of something like 100, which means there is a sudden change from pixel intensity from 0 to 100. So such type of change or such type of an edge is called as a step edge. The second type of an edge which we are going to talk about is ramp edge. So in ramp edge, instead of having an abrupt change in intensity, we are going to have a gradual variation in the intensity. So for example, I can have something like a pixel with the intensity of 0 and the nearby pixel can have an intensity of something like 5. Then the subsequent pixel will have something like 10. So like that, gradually the intensity gets increased or decreased and it reaches a maximum value. So such type of edge, we call it as a ramp edge. The third type of edge which we are going to talk about is ridge edge. So in ridge edge, there is a gradual increase in intensity and the intensity will reach to a maximum value and it will be retained for certain spatial positions. And then it starts to reduce to a minimum value. So such type of edge, we call it as a ridge edge. And the last type of edge which we are going to talk about is roof edge, where we have a gradual increase in intensity and the intensity reaches a maximum value, and upon reaching a maximum value the intensity starts reducing. So such type of edge, we call it as a roof edge. So all these types of edges can be identified by using a Canny edge detection algorithm. And this Canny edge detection algorithm is a multi-step algorithm, which means it has 4 steps. So the steps are provided here. So the first step is we need to apply Gaussian smoothing or blurring to an image. So a tutorial related to this Gaussian blurring and smoothing has already been uploaded in my website, so you can please have a look at it on how to use this Gaussian blurring technique on an image. So the main application of using this Gaussian blurring technique is it helps to reduce the noise. It helps to reduce the high frequency component. So thereby we can get more clear representation of an object. So after doing this Gaussian blurring, we try to compute the gradients. So gradients are nothing but the intensity variation in an image. So we can compute the intensity variation along x-axis and intensity variation along y-axis. So the gradient computation, on how to do this gradient computation, has also have been described in my YouTube channel. So you can please have a look at it. So we can make use of a Sobel kernel or scar kernel to compute this gradient in an image, where intensity variation along x-axis and y-axis. So the first 2 steps already we have discussed earlier in our earlier tutorial. So in addition to this, we are going to apply 2 more steps so that our algorithm becomes more robust and it can be able to eliminate the noise. So first let me talk about this gradients. So this gradients can be used to identify the edges in an image. But the problem with this technique is even noise, the edges of the noise will also be coming as an output. But we want to have the outline or edge of an object alone in an image. We don't want noise. So this noise will create unnecessary hindrance to our object representation. So we need to eliminate this noise. So in order to eliminate the noise completely, we are going to apply the step number 3 and step number 4. So step number 3 is nothing but we are going to apply a non-maxima suppression technique. From the name itself, we can identify that we are going to eliminate the non-maximum values. So after identifying the non-maximum values, we are going to eliminate it. So thereby the noises will get eliminated. So upon doing this third step also, still there will be much more noises will be there. So in order to eliminate the noise completely, we are going to apply a technique called as hysteresis thresholding, where we try to fix two threshold values, one is T upper and T lower. So by incorporating this hysteresis thresholding technique, we can eliminate the noise and we can retrieve the object in a much more effective manner. So we will see one by one the steps how we are going to do this Canny edge detection algorithm in detail. So the first step will be applying Gaussian smoothing or blurring technique to suppress the noise. After doing this, we compute the gradient magnitude and orientation. So gradient magnitude represents how much intensity variation is going to be there. So this is computed using this equation G equal to root of Gx square plus Gy square, where Gx is nothing but intensity variation along x direction, Gy is nothing but intensity variation along y direction. So upon taking square root on the square of these terms, we get the total magnitude variation. So this total magnitude variation gives how much intensity is getting varied, and we can also find the orientation. So orientation in the sense in which direction my intensity is going to vary, at what angle my intensity is going to vary. So that is computed using this equation, which is nothing but theta equal to arctan to Gy by Gx, and this value will be in terms of a radian. In order to convert it into a degree, kernels. So we have Sobel kernel and scar kernel. So we have kernels represented for Sobel, Gx and Gy. So by applying this kernel on an image and performing a convolution operation, we can able to get the intensity variation along x direction and intensity variation along y direction. So much more detailed explanation has been carried out in my earlier tutorial. Please, I recommend to watch that tutorial. So after doing this first two steps, we are going to perform the third step, which is our non-maxima suppression technique. So in non-maxima, what we are trying to do here, so here this technique, from the name itself, we need to find the maximum value, and that maximum value should be retained, the non-maximum values should be eliminated. So what is that maximum value? So maximum value in the sense, here we are not talking about the intensity, here we are talking about the gradient value. So gradient is how much intensity variation, right? So we need to compute the gradient magnitude for each and every pixels, and also we need to compute the orientation theta for each and every pixels. And after computing this gradient magnitude and gradient orientation, we need to do certain steps. For example, let us take a 3x3 neighborhood, and in that 3x3 neighborhood, I am going to see the orientation. So orientation means I am going to see in which direction my intensity is going to vary. For example, if my intensity variation is along north and south direction, I am going to examine the north and south pixels. If my orientation is pointing towards east or west, then we are going to examine east or west pixels. So first thing, after computing gradient magnitude and orientation, what we are going to do? We are going to look in what direction our intensity is varying or magnitude is varying. So if my intensity or magnitude is varying along north or south, we try to take north and south magnitude. If my intensity or magnitude is varying along east or west direction, then we are going to take the magnitude of east and west pixels. Then we try to compare it with the center pixel. If the center pixel magnitude is greater than both the pixels it is being compared, then we have to preserve it. If the center pixel or magnitude value is greater than the comparing pixels, then we have to retain it. If my center pixel is small, then in that case I have to discard it. So this is a simple algorithm to do this process. So let us try to visualize this in terms of an example. So first let me take example 1. So this is a gradient magnitude matrix. So all these values are G values, gradient magnitude values, which we get for each and every pixels, right? So here I am going to take the center pixel magnitude. So this is the center pixel magnitude, and when I try to see the theta value points in the direction of 90 degree. So it is pointing towards north pixel. So this is the north pixel, this is the south pixel. So since the orientation is pointing towards north, we have to take the north magnitude and the south magnitude. So I am going to compare the center pixel magnitude with the south magnitude and north magnitude. When I compare the center pixel magnitude with the south pixel magnitude, you can see the south pixel magnitude is small. In that case, we try to eliminate this south pixel. Then when I try to compare the center pixel magnitude with the north pixel magnitude, the center pixel magnitude is small. So we try to eliminate this center pixel. So like this, what we do is we try to eliminate the non-maximum magnitude pixel values. So thereby what happens? We try to retain only the pixel with large magnitude variation. So let me give another example. For example, if I take an edge, something like this, right? So here if I take a magnitude value of 10, the next pixel let us take it is 20, and the third pixel let us take it is 30, and the fourth pixel let us take it is again 20, and the last pixel is 0. So in this case what happens? I am going to compare with the neighbors, right? So here if I see, here I have a gradient magnitude which is maximum, whereas the neighboring pixels have a gradient magnitude which is less. So we are going to eliminate the neighboring pixels. So thereby what happens? My edge becomes thinner. Okay, my edge becomes thinner. So this process, non-maxima suppression, is also called as edge thinning process. So it is used to reduce the thickness of an edge, right? By eliminating the pixels with lower gradient magnitude, and we try to retain only the pixels where I have a gradient magnitude large. Let us take another example. So here again I show a gradient magnitudes. So this and all, it's a gradient magnitudes. So we try to compare the center pixel with the neighbors. So here when I see the theta, so theta is around 180 degrees, which is pointing towards west pixel, which means I have to take this west pixel magnitude and east pixel magnitude. So when I look at the center pixel, compare it with the west pixel magnitude and the east pixel magnitude, you can see that the center pixel magnitude is small. In that case, we eliminate the center pixel magnitude, whereas we retain the west pixel magnitude and the east pixel magnitude. So that is how this non-maxima suppression technique works. So this technique helps to minimize the noise, but still we are not eliminating the noise, right? So still some small amount of noise will be retained in an image. So in order to remove such information in an image, we go for a technique called as hysteresis thresholding, which is the fourth step in your edge detection process. So here what we do is we try to assign two threshold values. T upper and T lower. So remember, this T upper and T lower is also a gradient magnitude values, right? So we try to set the gradient magnitude values. So if our gradient at a particular position, is greater than the upper threshold, then that corresponding pixel should be an edge. Which means if my gradient magnitude is large, in that case lot of intensity variation is there. If I have lot of intensity variation, then that pixel should be an edge. So that is how the assumption is made. So here, if my gradient magnitude is greater than the upper threshold value, then that pixel is treated to be an edge. Same way we put another gradient magnitude threshold. So if my gradient magnitude is lower than the T lower, in that case we are going to consider that pixel as a not an edge, right? So this, if my gradient magnitude is greater than T upper, this will be treated as an edge. If my gradient magnitude is lower than the T lower, it will not be treated as an edge. It is not an edge, right? There will be some pixels with the gradient magnitude which lies between this T upper and T lower. In that case, what we do? So we are going to apply a condition here, right? So there will be some pixels with the gradient magnitude lies between T upper and T lower. In that case, for example, if I take B, where the gradient magnitude lies between T upper and T lower, in that case, whether this pixel will be an edge or not, how to make a decision? In that case, what we do? We look at the neighbor. When I look at the neighbor, if my neighbor is an edge, then I also should be an edge. For example, for B, if I look at my neighbor is also in between T upper and T lower. So we can't make a decision here. So again, I have to look at the subsequent neighbor. When I look at the subsequent neighbor, so this A is having a gradient magnitude which is greater than T upper, which means this A is an edge, right? Since this A is an edge, then the neighbor also should be an edge, right? Then the corresponding neighbor to that nearby neighbor is also will be treated as an edge. So we look at the neighbor, right? If our neighbor is an edge, then the pixel which we are trying to find a value should also be an edge. Same way, if my neighbor is not an edge, then the pixel value for which we are trying to find whether it is an edge or not also should not be an edge. So that is what we do in terms of your hysteresis thresholding technique. So here we try to apply a very simple technique. We try to put two thresholds, T upper and T lower, and remember, this is not pixel intensities, this is your gradient magnitude values. So I am trying to fix a gradient magnitude above which, if my pixel is having the gradient magnitude, then it will be considered as an edge. Below this gradient magnitude, if I have some value, then it will be treated as a not an edge. The pixels magnitude, gradient magnitude, if it is upper than T upper, it will be treated as an edge. If my gradient magnitude of a pixel is lower than T lower, it will not be considered as an edge. So thereby, by applying this hysteresis thresholding technique, we can eliminate the noise and we can retain the edges which are belonging only to a object alone in our image. So thereby, the edge of an object can be easily determined and it will be robust also. So now let us look at the implementation part. So here we are going to implement this edge detection algorithm in a Google Colab environment. So as I said, we have 4 steps. First step is applying Gaussian smoothing to an image to help reduce noise. Second one is we are going to compute Gx and Gy using a Sobel kernel or a scar kernel. Then apply a non-maxima suppression technique, and then finally we are going to define the T upper and T lower thresholds for your hysteresis thresholding. So let me explain the program. So here we are going to import the packages. So as usual, cv2 underscore imshow is used to visualize an image. Then matplotlib as a plotting tool, Python plotting tool, which can be used in our program if we want. Same way, argument pass is for getting the location of an image into a program. cv2 is computer vision version 2 library package, and numpy is for matrix computation. So after executing, after importing the necessary packages, I am going to upload a file from my hard drive. So I am uploading a file into the program, and the next step is I am going to read that image using cv2.imRead function. I am trying to read that image, convert that image into a grayscale image by using this function called as cv2.convertColor function, where I give the image and I specify that I am going to convert it from BGR to grayscale. So after I obtain a grayscale image, we are going to do blurring. So the first step in your Canny edge detection algorithm is blurring. So I am going to apply a Gaussian blur using this function called as cv2.Gaussian blur. I give the grayscale image and specify the kernel size. So when we try to do a Gaussian blurring, there is a sigma in the equation. So sigma gives how big is my width of the Gaussian pulse, whether I should have a narrow Gaussian pulse or a wider Gaussian pulse. So that will be determined by the sigma value. So that will vary from image to image. So it is very difficult for us to identify or determine the sigma value. So we will leave that task to the computer. So in order to do that, the sigma value which I specify here is 0, which means the computer will automatically compute the sigma value for us depending upon the input image. So then the blurring will take place using the cv2.Gaussian blur, thereby the noises will get submerged with the background, and then we try to see how the original image looks like, how the grayscale image looks like, and how the blurred image looks like. So when I execute this cell, you can see the output. Original image, corresponding grayscale image, and the blurred version. So you can see in the blurred version some details have been merged with the background. So there is a smoothing of the image takes place. So now we are going to apply the Canny edge detection algorithm. It is very simple. It's a very simple command. So the command is cv2.Canny. So here this cv2.Canny function takes 3 arguments. One is the blurred image, and we have to specify the t lower value and t upper value. Right? So this setting of this t lower and t upper plays a very important role, very vital role, that determines how many edges you will be able to identify. If you have a very big range, then more items will be identified as an edge. If you have a short range, then very less items will be identified as an edge. So you have to properly set this t lower and t upper so that you can get the required edges from an object. So here I define 3 different ranges: wide, mid, and tight. So where in the wide I am going to set t lower as 10, t upper as 200. In the second case, mid, t lower is set with 50 and t upper is set with 150. In case of tight case, t lower is set with 240 and t upper is set with 250. So we will see the outputs of this and we will try to analyze it, how it looks like. So and this outputs again I am going to see in terms of an image, wide, mid as well as tight. So when I execute this, you can see when the range is large, you can see more edges, right? You can see more edges in case of wide edge map and mid edge map, right? Whereas when the range are short, you can see lot of edges are being submerged or it is not able to be visualized. So the setting of this T lower and T upper is very, very important. So the range, it should be tunable, it should be tuned by the user, and depending upon the value, you should be able to get the proper outline. So you have to set a T upper and T lower to be an apt value. So that is how this Canny edge detection algorithm works. So the important thing to note here is, even though I have 4 steps, the first step we have to apply by using CV2.Gaussian blur function, and the second, third and fourth step, computing the image gradient, computing the non-maxima suppression and applying the hysteresis thresholding, everything is taken care by a single command called as CV2.Canny. So here in this tutorial, I described about the steps involved in a Canny edge detection algorithm. So there are 4 steps. First step is applying a Gaussian blur to an image, thereby noises will get merged with the background. And then the second step is computing the image gradient. After computing the image gradient, we have to apply the non-maxima suppression, and then after applying a non-maxima suppression, we have to apply a hysteresis thresholding technique. Thereby the edges of the object alone can be identified and the noises can be removed. Thanks for watching. Please subscribe for more technical learning. You can find the code in the GitHub repository link given in this slide. Thank you.